Okay, for warm-up, go ahead and work on this for about 7 minutes and pause the video, and when you guys are done, unpause the video. Okay, so we're going to go ahead and flip to the next page, all right, and we're going to talk about stoichiometry. So yesterday, I think you just flipped the packet over, right? Or no, flip the page. It's on the back of that. All right, so yesterday, if you remember, we really worked on conversions, right? So we did our intro to stoichiometry, which was just changing our units. And we learned about our little, what was our special guy that we learned about yesterday? What was our special conversion? Liters, right? So the 22.4 liters. And so we are going to be using that idea, okay? But really quick, before we just dive into this, when did they specifically say we can use 22.4 liters? Oh, so it's 1 mole, but it's at certain conditions. What were those? Right. So we're usually looking for STP or constant. Actually, no, it is just STP. Yep. So if it doesn't say STP, don't sit there and assume that. And we're going to learn a new way today of how you can deal with it when you don't have STP. Okay? And we're going to see that in a few. I also want to remind us about what we know with stoichiometry, where we have our railroad tracks, right? What's always important for us?
Down to the right.
Down to the right, right? We bring our words down to the right, and then we make a conversion up, okay? We also make sure when we're doing, so in stoichiometry, this is where we switch characters. So what do we always have to cross? A mole bridge, right? So we have our mole bridge or our mole ratio. And yesterday, I told you we weren't going to use it yesterday, and we didn't. But we talked about what can we use instead of moles? No, not grams. What was it? Liters, exactly. So now we also have this thing called a volume bridge, and it saves us a couple steps. We don't have to go through the mole. We can just go liter to liter because those coefficients are going to mean that, and that's what we're going to start with up here at the top, okay? So don't forget what you know about stoichiometry. Ooh, we're just going to move that out of the way. And yeah, okay. So for our volume-to-volume calculations, coefficients in the equation reveal volume, and that's the big change for gas laws. Okay, they are still moles, but we learned that through those guys' laws, we can directly relate them to volume as long as we have constant temperature and pressure. So that's a time saver for us. So looking at this, what kind of reaction is this, by the way? Synthesis. Good. All right. So let's go ahead and balance it. If you notice, we got 3 oxygens on the left, 2 on the right. So we're going to try and make this an even number by putting a 2 right there. So now we just got to balance our carbons, put a 2 on that side. Okay? So what is the mole ratio of this reaction? 2:1:2. Okay? And what we went over yesterday was that, yes, that's a 2:1:2 mole ratio, but now it's also a 2:1:2 liter ratio. Okay? As long as we're at STP. Okay, so this only applies to volume if all of the reactants and products are measured at the same temperature and pressure. So that's something that we've seen since yesterday. Okay, temperature and pressure have to be constant for this stuff to work. All right, if the volume of a gas in a reaction is known, you can calculate the volume of other gases in the reaction. And the way we do that is by using the volume ratio, what we just talked about. Okay, so maybe off to the side, since in my class we usually call it a bridge, you can put bridge off to the side. Okay, we usually call it our mole bridge. Now we have a volume bridge. Okay, all right. If the temperature and pressure remain constant throughout the reaction. So if we haven't said that enough, I don't know, tattoo it on your forehead. Okay, so for STP, what is the temperature? What is the temperature? 0 degrees Celsius. And we know that when we plug that into ideal gas law, it has to be in Kelvin. So don't forget 273 Kelvin. And pressure is 1 atm, or anything that's equal to that. Okay? Recall that your ideal gas equation is what? What's your ideal gas equation? It's on the board. Huh? PV equals nRT. Okay, so when we do gas stoichiometry, you're going to be using ideal gas law. That's another thing that's changing, okay? So ideal gas law gives us the mole part of our stoichiometry. So when we convert into moles, that's when ideal gas law is going to come into play, okay? Because that allows us to change this temperature and pressure to whatever we need it to be, not necessarily STP, okay? So recall that the mole ratio comes from the coefficients in a balanced chemical equation, okay? That's your liter ratio. Yes, ma'am. All right, so looking at our first problem, the combustion of propane occurs according to the following reaction. All right, so let's go ahead and look at this reaction that they're giving you. It's the first thing you should always check for when we give you a reaction. If it's balanced, good. So, is that one balanced? Yeah, if we usually put coefficients in there, we're not trying to trick you. So that one's balanced already, all right? Let's put a little check mark next to it. What will the volume in liters, oh, did not mean to cross that out. There you go. All right, what will the volume in liters of oxygen be for the complete combustion of 0.350 liters of propane, which is the C3H8, okay? All right, so one more thing I'm going to add to this. And when I taught you guys stoichiometry, I didn't really require you to sit there and tell me what kind of calculation it was, because we just did railroad tracks and we would end when we had what we wanted on top, right? For gas laws, because we're going to be throwing in the ideal gas law equation, I really want you, before you start solving anything, to tell me what kind you have, what kind of problem this is. So I'm going to scooch this up, okay? We are going from liters of propane, so I'm going to write that off to the side. Liters, C3H8. And really what I should be saying is volume, so that I know that's what I'm doing. Volume of propane. What are we going to? What does our answer want? What do we want our answer to be? Read the question. Good. Volume of oxygen. So I'm going to put volume of oxygen gas. All right. So this is a volume to volume. What that should tell you is it's a liter to liter. That's your mole bridge. This is the easiest one. This is like back in the day when you guys did a mole to mole calculation. It was just a one-stepper, okay? So let's go ahead and start solving it. We've got 0.350 liters of our little propane guy. Whoa. Okay. I'm still going to bring my words down and to the right. Okay. And I want to convert into liters of oxygen. Now, typically, back in the day, this would be when we would go moles on top, and then bring moles down, go back up, bring moles down, go to liters, okay? But what we know now is that we can use those coefficients for just a liter conversion. So we're going to make our bridge right here. And we're going to just go straight into liters of O2 because I have a balanced equation. Okay? When we go to fill this in, we are using coefficients because this is my bridge or my ratio. So looking at the balanced equation, what does propane have? A 1. What does oxygen have by it? A 5. All right, and you are ready to put that into the calculator. So go ahead and type that into the calculator. Oh, okay, 1.75, good. All right, 1.75 liters O2, and you're done, okay? So not too bad. So this one is pretty easy, but I want you to really make note that this is going to be your best friend in these calculations. Make your mole bridge there, okay? You don't have to go through moles, okay? All right, so let's look over at the next one, which I believe should be underneath for you, okay? All right, so now we're going to talk about when we have a volume to mass or a mass to volume. You guys should have a blank space underneath this part, right about here. And I want you to write a rule down for this, okay? ideal gas law is used where volume is located. Now, what I mean by that, okay? Ideal gas law is going to be used where volume is located. Typically, you're solving for moles in it. Once in a while, you'll be solving for volume, okay? But what I mean by that is that, you see these little words up here? Volume to mass versus mass to volume. I already told you on the last one, I want you to make sure you're making that label, okay? Once you have that label, wherever the volume is, that tells you what step you use ideal gas law. So for example, if we're going volume to mass, I start with ideal gas law to get moles, and then I do stoichiometry. If I'm going to volume, I start with stoichiometry, and then I plug in to get my final answer, okay? So, so pay attention to that. That's why I really want you guys labeling these, because this is the little trick to these, okay? Now, some of you are going to find that on a few of these, we don't necessarily have to use ideal gas law, but I want you to do it so that you only know one method, all right? You can go through the railroad tracks when it's all the same temperature and pressure and when it's at STP. That is the only time. So to get yourself into the habit, I would just go with ideal gas law for every single one. And that's how I'm going to teach you, okay? Are we all good? Okay, cool. All right, so filling in these little blanks, let's see. Find the number of moles of a gas given using the ideal gas law. Okay? And so they're showing you, so for a volume to mass, they're telling you use ideal gas law first, then go to stoichiometry the way that you know it. Okay? So let's go ahead and look across the page at the next question. Let's scoot this out of the way. All right, so your problem says, calcium carbonate decomposes according to the following reaction. Okay? So we're going to look at our equation. What's the first thing you should ask yourself? Is it balanced? Good. So is that one balanced? 3 oxygens on this side, 3 on that side, 1, 1, 1, 1. Yes, we are good. All right. How many grams of calcium carbonate must be decomposed? All right, so let's circle units, right? We want to know this. To produce 5 liters of carbon dioxide. Ooh, special, at STP. What that would tell me normally is that I don't have to use ideal gas law necessarily, okay? But we're going to on this one, okay? But STP tells us 0 Celsius, 1 ATM, okay? All right, so let's go ahead and write what kind of problem this is. What are we going from and to? Well, hold on. What kind of problem is this, you guys? We're going from 5 liters. So what is that? Volume. Good. So we got volume of CO2, and we're going to grams or mass, right? Let's put mass. Sorry. Mass of calcium carbonate, right? So what that tells me is volume is your first step, so ideal gas law is your first step, all right? So what would be most useful is solving for your moles. So we're going to take our gas law, PV equals nRT. How can I rearrange it to solve for N? Good, we're going to move these guys underneath. So we're going to end up with N is equal to PV over RT. Okay. Gotta squeeze this up here. Okay. And then once we have that, we're going to plug in. So my pressure, what is my pressure? It says add STP. So what's my pressure, you guys? 1 ATM. Okay. What's my volume that I'm starting with? We're finding moles of carbon dioxide in case you didn't know that. All right. What's my volume? 5 liters. Okay. My R, since we're using ATM, is what? 0.0821. Okay. And my temperature at STP? 273 Kelvin. Okay? All right, so plug that in and go ahead and shout out moles when you've got it. Okay, what did you guys get? 0.22. Can I get a second on that? Yeah? Okay. 0.22. And this is moles of carbon dioxide. Make sure you have it labeled. Now we can use stoichiometry because we're going to use that mole bridge. So now we're ready to change it into calcium carbonate. Okay? Because we're in the same language here. We're in moles. So I'm going to say 0.22 moles of carbon dioxide. Bring words down to the right like usual. Okay. What do I do next? I'm in Mole Town already, so what do I have to do when I'm in Mole Town? Mole bridge, we're going to cross the bridge. So I'm going to say moles of calcium carbonate. I changed characters, magic little bridge there. Okay. And we use coefficients in this one, right? So what are the coefficients for this? 1 to 1. Words come down to the right because that's not what they want our answer in. Remember, we want to get to mass. So we're going to see moles of calcium carbonate, and we're going to change it into grams of calcium carbonate. And just for time's sake, molar mass is 100.9. Okay, for every 1 mole. So go ahead and type that in, and let's see what answer we got. What's the answer? 22. That's it? Okay, grams of calcium carbonate. All right, so that's our answer. So we saw that we use ideal gas law in this one, okay? So let's look at the next type. Let me get you through that one real fast, and then you guys can practice. All right, so your mass volume. Okay, your mass volume. So now volume is what step? First or second? Second, right? So that means we're going to put ideal gas law second. So we're going to determine how many moles of unknown gas are formed. Okay, and then, so once we get our moles from using stoichiometry, then we move into step 2, which we are going to use the number of moles found and the ideal gas equation to solve for volume. Okay, so as you can see, ideal gas law is now second step. All right, so our problem that we're going to solve, tungsten oxide, whoa, get it? No, okay, all right. Reacts with hydrogen according to the following equations. We're going to look at our little balanced equation. She's not here. We're going to look at our balanced equation. This is H2O, by the way. It's kind of on the next line. Is that balanced for sure? Yeah, there's coefficients in there. So we're going to say, okay, cool. How many liters of hydrogen gas? So we know that we're looking for volume of H2 at 35 degrees Celsius and 0.90 ATM. All right, is that STP? No, okay. So this is one of those where this is why we use the ideal gas law. All right, it helps take care of that part. Are needed to react completely with 875 grams of tungsten oxide. So we're starting with mass of, whoa. Okay, so after we label it, now we know that we use ideal gas law second. So let's start with stoichiometry. Okay, so we're going to start with our 875 grams of, whoa. We're going to bring words down to the right. Okay, where do you want to go from there? Where do we go from there? So we're in gram land. So we can't do the ratio yet. We're still in gram land. What do we have to convert into? We have to go to mole town, right? So we're going to go mole of woe. And then we're going to bring words down to the right again. Now we're in Mole Town. We cross that mole bridge. And this is where you stop. Okay? Because now we have the information, oopsie, about my unknown gas right here. Right? That's who they want to know stuff about. So this is where we stop. Now let's plug in our numbers. We got 1 mole of this guy is, just for time's sake, 231.84 grams. Okay? And then down here, this is our bridge. So looking at my balanced equation, tungsten oxide has a 1, hydrogen has a 3. So let's go ahead and solve for moles of hydrogen real quick. And when you've got it, let me know. Okay, you should be getting 11.32? Yeah? Okay. 11.32 moles. All right, but we're not done yet. That's not what they want to know. We want to know how many liters. So now we're going to use our ideal gas law. And we are going to go ideal gas law to find liters. So we want to rearrange this to solve for which one of those variables? Volume, good. So we're going to move the P over. So we have volume is nRT all over P. And we're going to pay attention to our units so we know which R we're using, right? So N, we have moles now. We have 11.32 moles. That came from our answer. Our R. Okay, so we got to figure out what pressure they're using. We are using 0.980 ATM. So we're going to go ahead and go with the 0.0821 R because of the ATMs. And temperature. Temperature is given to us in Celsius. So somebody shout out, what is 35 converted, please? What is it?
308.
Awesome. 308 Kelvin. Okay. And then we're going to divide by pressure, 0.980. Okay? When you type that in, you should be getting, I'm just going to put the answer so you guys can check yourself, 292.09 liters of hydrogen. So make sure you get that answer. Yes, this is the final answer. Okay, so hopefully today you saw that you're using a combination of stoichiometry and your ideal gas law. We know that we use ideal gas law when we know if we're starting with volume or if we're ending in volume, okay? And so, yep, this is what's going to help us with the different conditions, okay? So once you've gotten 292.09, go ahead and turn the page. Or maybe flip the packet over. I think it's flip the packet over. Hold on 1 second. All right, and so now you're going to go ahead and work on these gas stoichiometry problems. You have a lot of space off to the side, and that's what that's for, okay? So that you can work through these problems. Here are the answers. Feel free to write them off to the side, but don't forget, label your questions. Label the type. Okay, because that's going to tell you wherever volume is, that's where ideal gas law is going to go. Okay? So you're going to practice this till the end of class. You have a quiz tomorrow over ideal gas law and just conversions, not stoichiometry yet. We're going to practice stoichiometry for another day. Okay? All good? Okay, this is not the correct answer. This is actually going for a question that is asking about the following. And I would rather you do the one that I'm writing. And it's asking if 75 liters of carbon dioxide are produced at STP, how many grams of O2 are needed. So that is actually going to give you this one. And I would prefer you do that over the other one because the other one's just the liters.